On the very first day of this unit, we talked about electromagnetic radiation being a wave. Maxwell said it was a wave consisting of really two sinusoidal waves, an electric field wave and a magnetic field wave. We looked at four different characteristics or four different properties of waves that are exhibited by EMR that kind of showed us that in fact EMR is a wave. We talked about refraction. We talked about polarization, and we talked about a couple properties that we've looked at in a lot more detail over the last couple of days, diffraction and interference. Those are all properties of waves. They're all exhibited by electromagnetic radiation. So EMR is a wave, right? It's settled, but it's not settled. Throughout history, people have been debating whether electromagnetic radiation or light is a wave or a particle. And there's been people on both sides of the fence. Hey, light's a wave, light's a particle. When we got to Maxwell and we came up with this electromagnetic theory that Maxwell came up with, and then we saw these properties of electromagnetic radiation that are exhibited by waves, and we saw Hertz's spark gap apparatus that seemed to verify Maxwell's theory of EMR, then it seemed like it was settled. EMR is a wave. And you know what? It is. We still think it is. But now, as of 110 years ago, we also think it's a particle. So we're kind of being fence sitters now. It's a wave. It's a particle. It's a wave. It's a particle. Which is it? It's both. Let's say it's got a wave nature and a particle nature. We're going to talk tomorrow about some evidence to support the particle nature of light. But today, we're just going to talk about the particle nature of light. The evidence comes tomorrow. The theory comes today. The theory is called Photon Theory. And it was first put forth by Einstein in 1905, 110 years ago. First time we've mentioned Einstein, eh? Physics 30, it's May. It's past the middle of May, and we're finally talking about Einstein. We're going to talk about him more as over the last few weeks of class here. Einstein had a year in 1905 unlike nobody else in no other year. Sometimes it's called the miracle year. He published four major papers, all discovering new things, all brand new ideas that nobody else had ever had before. Most people in their entire lives don't have a single original thought, a single original idea. Einstein had four of them in 1 year, 1905. One of them involved something called the photoelectric effect and photon theory, and this photoelectric/photon theory is what he ended up being given a Nobel Prize for later on. There's a few things that he could have been given a Nobel Prize for. Okay, the thing he's most famous for, the theory of relativity, never got a Nobel Prize for it. But this stuff he did. So you got to figure this is kind of important. Photon theory says this: light exists not just as a wave, but as a particle. The particle of light is called a photon. Now, we're not suggesting that this photon, this quantum of energy, this bundle of energy, rides a wave. Okay, I don't want you to try to visualize it necessarily. It's not a surfer on top of a wave. The particle is not on the wave. The particle is not following the wave. The particle, the photon, is the wave. Now, how do you visualize that? You can't, because that's outside of our experience. We've never seen a particle that is a wave, and a wave that is a particle. But even though we can't see it, even though we can't directly observe what a particle/wave would look like if we could see it, we have evidence to support the wave nature. We have evidence to support the particle or the photon nature, which tells us that it's got to be both. It's got to have a wave nature and a particle nature. Now, we can describe a photon mathematically. We can describe the energy of a photon, among other things. The energy of a photon is going to be equal to h times f. It's also going to be equal to hc over lambda. Where does that second equation come from? Well, we know v is equal to f times lambda, and in the context of EMR, v is c, the speed of light. If we rearrange that to solve for f, we get c over lambda, and if we sub in c over lambda for f, then hf becomes hc over lambda. That leaves us with one kind of mini mystery here. What's h? What's h stand for? H is a constant that we call Planck's constant. It was Einstein that came up with photon theory and explained this photoelectric effect with this photon theory, this particle theory of light. But a guy named Max Planck actually laid the foundations for quantum theory. Hence, he's the guy that gets the constant named after him, Planck's constant. Got to be given credit somewhere, right? The value of Planck's constant, the value of h, is 6.63 times 10 to the minus 34 joules seconds. Or, how can you have an or when you're talking about a constant? Or 4.14 times 10 to the minus 15 electron volt seconds. How can you have two different values of a constant? What's the speed limit? What's the speed limit on the highway? Jeff, what's the speed limit on the highway? 110 kilometers per hour. Kevin, what's the speed limit on the highway? 110 kilometers per hour. What's the speed limit on the highway, Ryan?
70 miles.
70 miles per hour. Good. You're both right. You're all right. Okay, it's two different numbers, right? About 70 miles per hour, right? 110 kilometers per hour, 70 miles per hour, two different numbers, but two different numbers that represent the exact same thing. Your car is going the exact same speed if your speedometer is reading 110 kilometers per hour because it's a Canadian speedometer, or if it's reading 70 miles per hour because it's an American speedometer. It's the same thing. We can have two different numbers that are exactly the same thing, and that's exactly what we have here. It's different units. That's it. Now, which one do you use? Usually, you use whichever one's convenient, whichever one you want. There are the odd time, couple of situations where you've got to use the first constant and not the second constant. But most times you can use whichever one you want, whichever one happens to be convenient. As we come across a couple of situations where we have to use the first one, I'll tell you about them. Right now, use whichever one you want, as long as it's convenient. Bottom line is this. If you use the first one, you're going to get an answer for energy in joules. If you use the second one, you're going to get an answer for energy in electron volts. If you have a multiple choice question and all four of your answers are in electron volts, you should probably use the second one because that's convenient. If all four of your answers are in joules, probably want to use the first one because that's the most convenient. Got it? I've got two examples that I want to go over today. This is the first of them. How much energy is carried by a photon of red light of a wavelength of 600 nanometers? Seems pretty straightforward, right? And it is. 600 nanometers is our wavelength. We want to circle the nanometers because we want to ultimately convert that to meters. Let's identify that as lambda, and we want to find energy here. So, all right, let's just say E is equal to hc over lambda. It's hf or hc over lambda. What value for h do you want to use here for Planck's constant? We get two values, and we're allowed to use either one. Which one do you want to use? Josh? Sorry? Joules? Okay, sure. That's probably the one I'd go with too. I'll tell you what. There are a couple situations where you got to use that one. This is not one of them. You can use whichever one you want here. But there are no situations where you have to use 4.14. So if in doubt, if you're not sure which one to go with the joules. Because that'll never lead you in the wrong direction. Okay, joules always works. Now you may have to do a conversion later on to get to electron volts if your four options are in electron volts, but joules will always work for you in the end. So let's use that. 6.63 times 10 to the minus 34 joules seconds times the speed of light, which is 3 times 10 to the 8. Divided by the wavelength, 600 times 10 to the minus 9 meters. Solve that, we get 3.315 times 10 to the minus 19. What are the units here? Vlad? Joules or electron volts? Joules, because we use joules right here, right? We should round that actually to 3 digits, 3.32 times 10 to the minus 19. All right, let's take a look at those 3 questions that go along with it. Give you just a couple minutes to work on those. All right, let's take a look at one more example here, and then we'll wrap it up for the day. 14.2 on 707 says, your eye can detect as few as 500 photons of light. So a single photon of light is light, but you're not going to see it. Right now, you're looking up at the front of the room, you're looking around, and you're seeing all kinds of things, bright things. You look outside, you know, the sun is bright outside, you're seeing the sun reflecting off of things. You're not seeing 500 photons of light, you're seeing thousands or millions of photons of light. 500 photons of light is the threshold. You can barely see at 500 photons of light. If you want to see something more, you need brighter light. You need more photons of light. But this is the threshold, okay? The eye is most sensitive to light having a wavelength of 510 nanometers. We're going to circle that because we want to convert that to meters. We want to know the minimum amount of light energy that your eye can detect. So this is our wavelength. This is our number of photons. And we want to find the energy. But we don't want to find the energy of a photon because you can't detect one photon. We want to find the energy that our eyes can detect. So what do we got to do? We're going to find the energy of 500 photons. Now, the easiest way to do that is to say, here's the energy for one photon, HF or HC over lambda, and then let's multiply it by 500. What do you want to use for Planck's constant? If in doubt, use the joules. 6.63 times 10 to the minus 34 joule seconds. Times 3 times 10 to the 8. Divided by lambda, which is 510 times 10 to the minus 9. Not so lucky this time. Sorry, that should be 10 to the minus 9, not 19. Not so lucky this time with our numbers. Can't do it in our head this time. What do we end up getting for the energy there of one single photon? You get 3.9 times 10 to the minus 19. And that's going to be in joules, right? Because what we use right here is joules. Now we're going to multiply that by 500. And when we do, we should get 1.95 times 10 to the minus 16 joules. So one photon, 500 photons. We're looking for the energy of 500 photons, the minimum energy that our eyes can detect. All right? Got a couple questions to go along with that as well. We've got now, over the period of the last hour or so in class today, we've dealt with a few sets of practice problems. Page 693, which you may have finished. If not, finish them up tonight, please. Page 706, which, again, you may have finished those up. Those are the ones you were working on a few minutes ago. And finally, page 707, it's these ones here. Now, these two sets go very, very quickly, just the photon stuff, right? This one, not quite as quickly, but not so bad. It's 9 questions. Okay, but you got some of those done already, and I think that for the most part, they should go pretty quickly for you.